Here's another example of being able to dissect the equation of a quadratic function and turn it into the graph of this and be able to identify the key features. So we have this function, g of x equals negative x squared plus 8x plus 1. First thing we have to do is we have to find the vertex. And notice it's not in standard form, but you might recall that there was a formula for the vertex, which we're going to use. And the formula for the vertex is negative b over 2a, and then the function at negative b over 2a. All right, so, and in this case, we know that b is going to be 8 and a is negative 1. All right, so that's just the coefficients of the x squared and the x term. And so for the x coordinate of the vertex, that's going to be the opposite of b, which is going to be opposite of 8. And then we're going to divide that by 2 times negative 1. If we compute that, that just becomes positive 4, because we would get the opposite of 8 over negative 2. So that's going to be 4. And then if we wanted to figure out what the y coordinate was, y is going to be when we plug 4 back into the original function. So that's going to be the opposite of 4 squared plus 8 times 4 plus 1. And if we compute that, that's the opposite of 16 plus 32 plus 1. This is going to be 16, and one more is 17. And so our vertex is going to occur at the point 4, 17. Okay. Now, so that's part I. For the second part, we have to determine whether the parabola is going to be concave up or concave down. And if you recall, that's where we look at the value of a. And we already defined a in this case to be 1, or negative 1, excuse me. And again, a is going to be the coefficient of the x squared term. And so that's going to be, since a is equal to negative 1, which is less than 0, that means that this parabola is going to be concave down. Okay. By the way, at the end of this video, I'm going to show you how to put this into standard form, okay, or the general form. But for right now, I'm going to show you the more basic ways to be able to get these components. Right? Third part is to determine if we have a max or a min for the parabola. And since a is equal to negative 1, which is less than 0, that means we are going to have a maximum. Okay, so we have a maximum. Okay, and so if I'm just drawing a really simplistic picture, it's going to have one of these sorts of shapes. Okay, so we have this maximum right here at the vertex. Okay, and I know that's not, it's not even close to what the actual parabola looks like, but that's what at least the general form should be. Right? We need an axis of symmetry, and so for our axis of symmetry, all we do is we just take a look at the x coordinate of the vertex, and we just say x is equal to 4. All right, so basically, if I look to the right and to the left of x equals 4, the parabola should look exactly the same on those sides. Right? Fifth step is to determine the domain and range. Recall from the previous video, the domain of any quadratic function is all real numbers. Okay, so that makes it really easy for us. Okay, so we don't have to worry too much about the domain. What I have to do is make sure I can write it correctly. So x is an element of negative infinity to positive infinity. Okay, however, if we want to figure out the range, okay, that's where we might want to graph it. Okay, so I'm going to go down here. All right, and I'm just going to make a really simplistic graph of this. All right, so we have the point 4, and let's just say 17 is somewhere up here. And recall that this is a maximum, and it's going to be concave down. All right, again, that's just a basic sketch. That's no way indicative of what a correct sketch would look like. So notice that the parabola just keeps going down towards negative infinity. And then finally, at this point, 417, it stops. Okay, so right there is going to be the maximum of this parabola. Okay, and so for the range, what we would say is that y is going to be an element of negative infinity up to 17 inclusive. Okay, so that's not so bad so far. Okay, and these are the most important parts of the parabola aside from the intercepts. Now, the intercepts are a little bit tough to get. So let's go ahead and try to identify those. For our intercepts, the easier of the two is to find the y-intercept. Okay, so for the y-intercept, that's going to, remember, be where we find, in this case, g at 0. Okay, and this is actually really easy for us to find this time. So g at 0, and remember, our original parabola was negative x squared plus 8x plus 1. So we would have the opposite of 0 squared plus 8 times 0 plus 1. And clearly, that just becomes 1. Okay? And so the intercept of this function is at the point 0, 1. Okay? Or if we were just asked for the y-intercept, that would be equal to 1. All right? But it's probably more important for us to have the coordinate or the ordered pair. Now, our x-intercept is a little bit nastier, but it's not so bad as the last one because it's already expanded for us. And remember, for the x-intercept, that's where y is equal to 0, or in other words, g at x is equal to 0. And so 0 would be equal to opposite of x squared plus 8x plus 1. All right, so let's throw it into our quadratic formula. Okay, remember, just to write it out, quadratic formula, negative b plus or minus the square root b squared minus 4ac under the radical divided by 2a. And so in this quadratic, we can clearly see that a is negative 1, b is 8, and c is positive 1. Okay, so keeping those in mind, then x is going to be equal to the opposite of 8 plus or minus the square root of 8 squared minus 4 times negative 1 times 1. And we're going to divide that by 2 times negative 1. All right, just throwing everything in. Now we're going to simplify. So x is going to be negative 8 plus or minus the square root 8 squared, 64. 4 times negative 1 times 1 is going to be 4. In the denominator, we have negative 2. And so this just becomes 68. Okay, so this is going to be the square root of 68, which should have a common factor of 4 if we elected to simplify it, and we should simplify it. Okay, so we know 68 is going to be 4 times, I think, 17. All right, but we can certainly use a calculator to check that out. Let me go ahead. And just to remind you guys that if you wanted to use a calculator to check out the factors, I'm going to say Desmos Graphing, or just Desmos Scientific Calculator. And I don't want graphing calculator, I just want the scientific one. Maybe. Okay. Remember, what you can do is you can just divide things out. Okay, so you could just take that 68 and then divide it by 4, and that's going to give you the 17. And notice that 17 is a prime number, so that means that 4 is the highest of the perfect square factors. Okay, if we got something like an 18 that had a factor of 9 in it, then we'd probably have to go a little bit higher than that. Okay, so we can write this as root 4 times root 17, or 2 roots of 17. And you might be asking, well, why do we have to do that? Okay, so let me show you why. We're going to get negative 8 plus or minus 2 roots of 17 over negative 2. And notice that everything is divisible by negative 2. Okay, in fact, we could just cancel everything out. Okay, and so this is going to end up being negative 8 over negative 2 plus or minus 2 roots of 17 over negative 2. And so our x-intercepts are going to occur at the points 4 plus minus, these twos are going to cancel out, root 17. Okay? And so our two intercepts are going to be 4 plus root 17, comma 0, and then also 4 minus root 17, comma 0. All right, and then if we got an approximation for these, which is probably going to be best for us, let's just go into our calculator and do that. That would be 4 plus root 17, and that's going to give us 8.12. I'll just say 8.1. So that's going to be 8.1 comma 0, and then let's say 4 minus root 17. I could just change this to a minus really quickly, and that's going to give us negative 0.1. Okay, so really close to the axis. So that's going to be negative 0.1 comma 0. All right. Now, my math lab's going to ask you for this. when we graph this in real life by hand, we're probably just going to use this right here. And so let's verify whether or not all of this makes sense by plugging it into our graphing calculator. Okay, so remember our original function, we had y equals negative x squared plus 8x plus 1. All right. Now, I'm going to go through, and remember we said the vertex. Okay, I'm going to zoom out a little bit. And we also had the axis of symmetry was x equals 4. All right, so notice it splits it right in half. Let's plot the point 4, 17, and that's going to be our vertex. Right. Let's also plot the point 0, 1, which was going to be our y-intercept. Okay, so that's right there. Let's also plot the intercepts. Okay, now I'm just going to plot them in the approximate form. So remember, we had 8.1 comma 0, right? And it looks like it's right here on the axis. The other one that we had was negative 0.1 comma 0, all right? And there we go, okay? And those points are both on the x-axis, okay? Notice also it's concave down, all right? And it matches up with the domain and range. And by the way, I think if I wanted to, I could go ahead and type in, what did we say, 4 plus the square root of 17, all right? And then we get the exact, well, this isn't exact, but it's a better approximation. And then we could just go ahead, take this and plot it right here if we really wanted to, change that to a minus. And there's the other x-intercept, okay? So that's actually really cool that now what we can do is without using any sort of technology, we can find all of those really cool sorts of components of the quadratic function, okay? All right, now I'm going to stop this video, and the next video, what I'm going to do is I'm going to show you how to put this into standard form, okay? And then I'm also going to go through one last example of being able to work with quadratics before we actually find the equation of the quadratic in standard form given the graph.